occurs when the instruction depends on the result of a prior instruction that is still in the pipeline. Okay. So, for example, we will see in this set of instructions, okay, add R1, R2, R3. That means R2 plus R3 will be written into the register R1. In second instruction, subtract R4, R1, R5. That means R1 minus R5 will be into R4. That means you can see here we are writing, producing the value of R1. Here we are using the value of R1. Okay. So here dependency occurs. Okay. Then the third instruction, we are using the value of R1. In fourth instruction, we are using the value of R1. In fifth instruction, we are again using the value of R1. So when we will draw the time fetch diagram for this, so our instruction at clock cycle 1 fetch, clock cycle 2 decode, clock cycle 3 execute, 4 clock cycle decode to the memory stage, 5th clock cycle goes to the write back. So that means here we are producing the value of R1. At the write back stage, we are writing to the register R1. Okay, we are writing the register to the R1 at write back stage. Now, for the second instruction, fetch, decode, execute, memory, write back. So it's completely 6. The problem is what? Here we are reading the value of R1 and R5 at which stage? In decode stage. We are reading the value of R1 and R5 at the decode stage. So our concern is regarding R1, so I am writing here. We are reading R1. Okay. Say for the third clock cycle, we are reading R1. For the division, here we are reading R1. For last instruction, we are reading R1 here. But problem is what? We are producing the value of R1 at 5th clock cycle. Yes or no? We are producing the value of R1 at the 5th clock cycle. But second, third instruction and fourth instruction, using the value of R1 at 3, 4, 5. Yes or no? So here you can see we will get the wrong value of R1 at third clock cycle. At fourth clock cycle, we are again will get the wrong value of R1. Now what about this one at 5th clock cycle? Will we get correct or wrong? Will you get correct or wrong? We will get correct. We will get correct. Why correct? Why correct value? Because reading the register and writing into the register, we are doing in the half of cycle. Half of cycle. In the first half of cycle, we are doing writing register. In the second half clock cycle, we are reading the register. Okay, that means here we are doing writing to the register in half of clock cycle. So here in the half of cycle, in the second half clock cycle, we are reading the register. So here we will get the correct value, but here we will get the wrong. Again here we will get the wrong, but here we are getting the correct. So here is also correct because it is occurring at the 6th clock cycle. Okay. For the instruction 2 and 3, we are getting the wrong value of R1 because it is produced at the 5th clock cycle. Okay. So at clock cycle 3 and clock cycle 4, we will get the wrong value of R1. So what is the solution for this? What is the solution for this data hazard? So there is 3 solutions: stalling, operand forwarding, last of the instruction reordering. So we will discuss one by one. So first stalling. So for the same instruction set, we will draw the time phase diagram. Okay, by using stalling method. So the instructions are there: add, subtract, multiply, division, subtract. Okay. So all other places I am not writing fully dotted but okay. Let's say draw the time phase diagram. At clock cycle 1, it will go to the instruction fetch. 2, instruction decode. Second instruction will go to the instruction fetch. Third clock cycle will go to execute. Now ID. Okay. Third instruction will go to the instruction fetch. Fourth clock cycle will go to the memory. Now I cannot do execute here. Why? Because ID is not yet completed. Why? Because the dependency. Because of the dependency. The value of R1. Okay. So when it will produce at the right back stage. So up to that we will make stop the pipeline. So as ID is not completed, so it can, so third instruction cannot go to the ID stage. So here it will be stop. Okay. At fifth clock cycle, it will go to the right back. Now stall. So again stop. At sixth clock cycle, now it can do execute. Because here we get the correct value of R1. Now, so when ID is free, now third instruction can do the ID stage. Now IF is free, so fourth instruction can go for the IF stage. Okay. Now just complete it. Seventh, memory, EX, ID. Okay. This is it. That means we are making two stalls here. Okay. So you will write. So two stalls are there. Two stalls. And how many clock cycles is required? 11 clock cycle to complete the instruction set. 11 clock cycle required to complete this instruction set. Okay. So when you are when you are drawing the time phase diagram, just see where we are producing the result at right back. Okay. After that we can start execute. After that we can start execute. Not before that. If you do before that, then you will get wrong result. Okay. So after the write back, you will start the execute stage. Okay. Why to stall? To stall because if you do the execute here, then it will get the wrong value of R1. 11 clock cycles are required to complete the instruction set, and those stalls are there if you are using the stalling method.